Hey guys, happy day to you. I'm going to say happy Monday. I'm not sure if you're listening to this on Monday or not, but we are now entering week 9 of our Chem 20 distance learning. So guys, this first podcast is going to continue on with the stuff we've been doing the last couple of weeks. Here's the deal. We are in end times, and it's really important that if you have any intention of going into chemistry 30, that you're taking these weeks seriously, because we're building on science 10 skills with reactions, balancing, and predicting. And of course, states of matter solubility. And then we're also now learning something new with the stoichiometry. All of these guys combined are beyond essential for you to have success in Chemistry 30. So please work at it, listen to the podcasts, take the time. Think of it this way. If we were in school, you would be spending 80 minutes with me 4 days a week, another 50 on Friday, plus some work at home. So even if you're spending 3 hours on this a week, it's a whole lot less than what it would be in school. So take some ownership, work hard at it. Here we go. All right. Now, our focus today is going to be still on stoichiometry. And stoichiometry means that you're looking at mole ratios from a balanced chemical reaction and then essentially comparing the amount of one reactant or product to another reactant or product. This one has a fancy word with it, gravimetric, and that just means let's not just look at amounts, but let's then convert those amounts to masses. This is not an unfamiliar concept, guys. When you compare quantities of an amount, in other words, of one reactant to a product in the same reaction, well, there's of course a variety of different formulas we can use to do that. And I reminded you of those a couple weeks ago when we were reviewing how to do different amount calculations, right? So now with gravimetric, like I mentioned, our focus here is on masses. So in terms of a direct comparison, we got to compare the moles. That's all we can do. And we have to revisit that concept I introduced you to at the end of last week with mole ratios. If we want to compare mass to moles, how does that work? Okay, well, let's start to go through a process. Now, coefficient ratio, like I said, notice I'm harping on this, hence it's important, compares amounts. In other words, number of moles, all right? So if that's what our coefficients do, then if we look at this example right below here, the formation of carbon dioxide gas, it's balanced, no problem. We would say exactly 1 mole of solid carbon reacts with exactly 1 mole of oxygen. That's a mole ratio, 1 to 1. But it would be completely wrong to say 1 gram of carbon reacts with 1 gram of oxygen. So moles are not equivalent to mass. In other words, 1 mole does not equal 1 gram. Not at all. Guys, 1 mole is completely related to our periodic table, right? So if you check off the periodic table, and I'll blow up a little bit here, 1 mole of oxygen by itself is 16. 1 mole of oxygen gas, 32.00 grams per mole, right? That's what 1 mole is. 1 mole of, say, germanium is totally different. Germanium has a mass of 72.64 grams per single mole. 1 mole of krypton gas is 83.80 grams. So obviously 1 mole is not equal to 1 gram. This is not a new concept. When you do these, very similar to what we did last time, in that step 1 is of course going to be write the chemical equation, but make sure that it's perfectly balanced. So you can see all of our skills that we've been developing are really important here. Proper predicting of naming, proper prediction of reactions, figuring out the balancing after that, etc. Now from there, we figure out the number of moles of what we'll call the given substance, right? So this would be N of our given amount, right? Now, like I said, it has to be about the moles because that's what our coefficients are balancing. Once we have moles, this is what I was referring to from the gravimetric perspective. We can then convert it with a super familiar formula into mass, or vice versa. We could take a mass and convert it into moles. If we rearrange this formula, we end up with mass equal to number of moles times molar mass, right? So you can go back and forth between them. All right, let's keep going. From there, once you have figured out the given number of moles, remember you might have to convert to do that. Now we need to figure out, based upon what you were given, how many moles do we have of what the whole question requires. And this is the whole idea of using the mole ratio. And all I mean by that, guys, is look at the number of moles that are required, that you're looking for, and do a ratio between that and the moles you were given in the question, right? When you figure those out, it's a simple matter of then making a ratio here to figure out what X is, right? You'll have this number as well. So you're going to multiply, figure out the mole ratio, and eventually get an answer for X, okay? When you are then calculating potentially the mass of the required substance. So let's say you end up doing the mole ratio, just like you did last week, you get the moles. There, you got an answer in moles. Well, a lot of times the question needs to go a little bit further. So I might say, okay, yeah, you've got moles, awesome, but you need to take that and substitute it into this equation, right? This rearrangement right here to then solve for mass, right? So it's a back and forth process. All of a sudden, doing a single calculation isn't going to exist anymore. All of these questions are going to start to become multi-step, a little bit more time consuming, and a lot more that has to be at attention to detail. Are you calculating your molar mass properly? Did you balance properly? Did you predict your products accurately? So many things that you need to be taking some time, double checking, slow down, work at it. Okay, let's do some examples, because no better way to actually understand this. Hard thing with these sometimes for people is figuring out what are you given, what are you looking for. So I'm going to use some different colors, highlighters here then. Mass of oxygen, so we know we're looking for M of oxygen. And we are given a mass of another substance, this ethane. Okay, so we've got a given, and we've got what we're required to find. We're required to find the mass of oxygen. We're given the mass of ethane. Well, the only way to do this is step one, get a balanced chemical reaction. What type of a reaction? There's a hint. It's built right in here. Burning. If things burn, more specifically a hydrocarbon in the presence of oxygen, ding, 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 we have combustion. So let's build this balanced chemical reaction. We've got C2H6 gas reacting with oxygen gas. And of course, it's going to produce its complete combustion, CO2 gas and water vapor. Now, guys, a lot of people struggle with balancing combustion reactions. A really good way to do it is automatically just double the hydrocarbon. You might have to reduce it again afterwards, put the numbers back down, right? Make sure that you can factor something out, but starting with this helps. This way we've got 4 carbons reacting, 4 carbons being produced. Do oxygen last, so go to hydrogen next. 12 hydrogen reacting. I'm going to need 12 produced, so I'll put a 6 here. Now I'm up to 6 plus 8 oxygens, which is 14. So to get to that, I put a 7 here. Look at the numbers, 2, 7, 4, 6. Can you reduce those? Nope, it's done, okay? Alrighty. Next step that I like to do is I'll write down my givens. So what do I actually know? Well, first I'm looking for the mass of oxygen. That's the point. Notice I'm writing it under the oxygen. I'm trying to keep organized. Ethane, on the other hand, 120 grams is the given. So I'm going to write that right under the ethane. Mass equals 120 grams. For both of these guys, you have another given, the molar mass. It's not in the question itself, but with those formulas, you can sure figure it out. Calculate it out for ethane, you would get 30.08 grams per mole. And for oxygen, it's 16 times 2. We get 32.00. Sig digs, the zeros need to be there. Grams per mole. Okay. Now, again, think about it. How do you get the number of moles of the required to then use the mole ratio to get the number of moles of the... how do you get the number of moles of the given to then use that for the required? Well, given is ethane. So let's start working through that one. We have a formula. N is equal to mass over molar mass. Super familiar formula. Nothing new there, guys. It's just that we're going to have to perform these calculations more than once. So mass divided by molar mass. Here's a big deal. Take note. Pay attention. Do not round. Do not round to the very, very end. We're going to have multiple numbers that we have to use a multiple number of times. Don't round them. If you do, you will get all these answers wrong. Okay? If you are off by 1 decimal in your final answer, I'll mark it wrong. Don't round till you're done. All right, here we go. Speaking of which then, we can now get for this the number of moles of the ethane, the C2H6. It is equal to, unrounded, 3.989. The number keeps going on my calculator, moles. All right, so here's now where we do what we did last week. That's the point we're at. This is what I would have given you last week. This time you just had to calculate it first with a mass that you were given. So we take this and we need to go to the mole ratio. There's our next step. Okay, so mole ratio from this says we're looking for the oxygen, right? So we say, okay, the ratio of the oxygen gas to the ethane gas, and I look at my form or balanced equation here, right? And I go, okay, my ratio is a 2:7 ratio. That's what I have to compare. So, okay, there are 7 moles of oxygen for every 2 moles of ethane. And I just worked out the 3.989 moles of ethane. So that goes on the bottom. 3.989 moles. Here's my unknown, the oxygen. So cross multiply, divide, nothing new there. This is just like we did last week. We're going to have 7 moles times 3.989 moles divided by our 2 moles will give us X. Moles cancel out, we'll be left with moles. Perfect. Number crunch, get what you get. Do not round. And what this will represent is the number of moles of oxygen. And it is 13.9627 moles. Now, guys, I said this before and I'll say it again. Please pause the podcasts, take the time, number crunch yourself, put things into your calculators. Imagine you were in class and we were going through that process, right? Okay, so now what we just did is got the number of moles of oxygen. We're still not done because the whole point of this question was the mass of oxygen, and we don't have that yet. But if we've got the number of moles of oxygen and we got figured out previously the molar mass of oxygen, well, we're good to go. You can now definitely get your mass. So we're going to take this number of moles and we're going to say, all right, mass is equal to number of moles times molar mass. Use the number you just find, the unrounded, 13.96 ... moles. It should still be in your calculator. Times the molar mass of oxygen, 32.00 grams per mole. Number crunch away. You're going to get a long number, but you need to look at significant digits. We started with 120 grams of ethane. So 3 sig digs. The mass of oxygen will be 400, round properly, 47 grams. Done and done, guys. So lots of steps happening, okay? Lots to keep track of. Think about what's what. I don't think you can wing your way through this one. Do the work, learn the material, then you can process it. And again, if you have any aspirations of Chem 30, you cannot ignore this. You will not pass Chem 30 if you can't do reactions, properly predicting formulas, properly predicting states of matter, and stoichiometry, okay? You need to take the time to learn it. I'm 100% confident every single one of you can learn this and has the capability, but you're going to have to put in the time. Okay, let's do another example. This one, read through, pay attention to what you're given because you have to build a reaction here. That's step 1. We are given a solid lithium hydroxide, and then it reacts with carbon dioxide gas. Notice I'm giving you states of matter in the context of the question. Take advantage of that. Then it says this is going to produce And I think in your notes it says a solid lithium carbonate. So I'm giving you products. And it also produces water vapor. The whole point of the question is what mass of lithium carbonate is going to be produced. So that is what we're looking for, right? That's going to be our required, what we want. And we're given that 5 grams of lithium hydroxide is used up. There's our given. Okay, this is a mass stoichiometry again. How do I know? Because I'm given a mass and I'm looking for a mass. First step, balance chemical reaction. All right, let's start to build this thing. Balanced, balanced, balanced. You forget to balance, we're going to have issues. We have lithium hydroxide. Question says this is solid. Added to carbon dioxide gas. This is not a familiar type of a reaction. It's not double replacement. It's not combustion. That's why reactants and products are given to you. Next part that says is we're producing solid lithium carbonate. Oopsies, there we go. And we're producing water vapor. Okay, there's our givens. Balance this thing. We have 2 lithiums produced. We need 2 lithiums to be reacted. Everything else works out. 4 oxygens, 2 hydrogens, we're good. Start to write down what you know and what you're looking for. Whole point of the question, what mass of lithium carbonate is produced? Mass equals we don't know. Given 5 grams of lithium hydroxide reacts. Mass of the lithium hydroxide, 5.00 grams. Don't forget, 2 other things that are given to you are those molar masses. So calculate them, figure them out. This is one of those steps that is worth double checking. Number crunch them twice, because if you get them wrong, the whole rest of the question is wrong. And that's a huge pain. So number crunching, molar masses twice, well worth your number. Molar mass of lithium carbonate is 73.89 grams per mole. Okay, in terms of where to start, well, honestly, you don't have enough data to start with the lithium carbonate. That's where your unknown is. You do have enough information to figure out the number of moles of lithium hydroxide. So start there. Okay, here we go. N is equal to, yes, show your formulas. Yes, show your substitution. Yes, show your units. Nothing new. Same process we've been doing all the way through. 5 grams divided by 23.95 grams per mole. Grams will cancel out. Left with moles. We're going to have number of moles of lithium hydroxide equal to 0.0. Oops, no, not 0.0. Let's try that again. 0.2087 keeps on going moles. All right. How do we get this number of moles to determine the number of moles of the lithium carbonate? Okay, look at it. We now have moles. We can use the mole ratio. That will not give us mass. Moles is different than grams, but we can still go through the step by step. All right, going through this then. My mole ratio here states that the lithium carbonate, the required what I'm looking for, compared to the lithium hydroxide is equal to a 1 mole to a 2 mole ratio. And again, the way that I got that is I looked at what's in front. This is a 1. There's nothing written there, but it's like in math. We're lazy. We leave off the ones. This is a 2. That's where I got that 1 to 2. Okay, equals, and I don't know how many moles of lithium carbonate I have. That's my whole point of my question. But I do have a value we can plug in for the lithium hydroxide. It's the one we just figured out, 0.2087 ... moles. There it is. Cross multiply and divide. We're going to end up with X equal to 1 mole times 0.208 ... moles divided by 2 moles. Moles cancel out, number crunch away. Remember, do not round yet. The number of moles of the lithium carbonate produced is going to be 0.10438 ... moles. You're not done. Remember the point of the question. Find the mass. Don't find the moles. So now we can take that number of moles that we just determined and we can use that to figure out the mass. Rearranged formula, mass is equal to number of moles times molar mass. Number of moles I just figured out, 0.104 ... moles. Molar mass of that lithium carbonate we got before, times 73.89 grams per mole. Plug it in, number crunch, we get that the mass of that lithium carbonate, watch your rounding, we need 3 sig digs, 7.71 grams. Done and done. Okay, there it is, guys. I cannot emphasize enough. Double check your work, take your time, double check your proper prediction of reactants and products, that you've correctly written formulas, double check your balancing, double check your molar masses. Take the time, otherwise easy mistakes are made. Let's do the last example from the notes. In this situation, we're trying to figure out the type of a reaction. Solutions is noteworthy. Yes, things are going to be potentially aqueous. And we have a solution of sodium bromide mixed with a solution of lead-2 acetate. Ding, 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 guys. 2 ionic compounds. This is a double replacement reaction. In the end, once that happens, we get a precipitate, so a solid will be formed. There's a hint. That precipitate, you don't know what the formula is for it yet, has a given mass. Now, the whole point of the question is what mass of lead-2 acetate was actually dissolved to do this? That is our required. That's what we're looking for. Let's make a balanced equation, of course, to start. Get used to it. It's where we always begin. We have sodium bromide. Both are a +1 or -1 ion, so it becomes NaBr. They're both in solution. The reactants for double replacement reactions always will be. So sodium bromide aqueous plus lead-2 acetate. Lead has a 2+ ion. Acetate is -1. So here is our formula for that with a 2, and it is aqueous. Double replacement. Your metals are going to swap places. So our sodium and our lead are going to switch out. We're going to end up with sodium acetate, like such. We'll figure out the states of matter momentarily. And we're going to end up with lead bromide. Make sure you balance your charges properly. When you check your solubility table, we would go, I'll just do this once. Let's go to acetate. We check it out. It's right here. Is lead listed in this section? No. Or sorry, is sodium listed in this section? No. Therefore, the sodium acetate is going to be aqueous. Vice versa, let's look at the lead bromide. Find that bromide. Whoops, I scribbled it out. That's not what I meant to do. There we go, bromide. Let's look for the lead, and sure enough, lead is here. Therefore, yes, this is going to be your precipitate. This is going to be solid. That's huge, because in the question it says, the precipitate has a mass of 2.17. You didn't know that until you figured out what the precipitate was. Now we can put that 2.17 grams in the proper location. What are we looking for? The minimum mass of lead-2 acetate dissolved. There's our unknown. Remember those extra givens you can always figure out. Molar mass, 325.3 grams per mole. Lead's a weirdo. Lead does not have 2 decimal places for its molar mass, which means anything with lead, we only have 1 decimal place for molar mass. Same thing applies for lead-2 bromide here, which is going to have a molar mass of 367.0 grams per mole. Okay, our thing we're looking for is this, the mass of lead-2 acetate. Our givens, we have enough information to now figure out the number of moles. So we're getting somewhere here. Uh-oh. Bah! How do I get back? Like that? Yeah, open it. Oh, okay, good. Sorry. Right. N is equal to our mass over molar mass. Same. So we're going to take that, 2.17 grams, divided by 367.0 grams per mole. Don't round anything. We'll round later. N of our lead-2 iodide, unrounded, is 0.005912. I kept the number on my calculator. There it is. We take our mole ratio. Guys, do you see the pattern? but you do need to practice these for you to be able to get them. Yes, there's patterns, of course. Alrighty, what we are looking for is the lead 2 acetate. So I'm going to write that on top, CH3COO2. And on the bottom, I'm going to put what I'm given. And I do have the number of moles, we figured it out, of the lead 2 bromide. Look at that ratio between the two. Do you see what I did? I forgot to balance. We have to balance every time. So 2 here, my bromides are going to have 2. There we go. Okay, this is a nice, lovely, easy ratio. It is a 1-to-1 ratio. Beautiful. 1-to-1 ratios are lovely because they end up being the exact same number. The mole stays consistent. How do I know? Well, you can prove it. 1 mole over 1 mole is going to be equal to X over what we calculated, 0.0059 ... moles. Think about this. When you cross multiply and divide, guys, you're going to end up timesing by 1 and dividing by 1. Oh, easy peasy. So that means our X, which in other words is the number of moles of our PbCH3COO2, right, our lead 2 acetate, is going to be equal to the same thing, 0.0059 ... moles. It's a 1-to-1 ratio. This number I can now use to figure out the mass of the lead 2 acetate because I have the moles, I have the molar mass, we're good to go. Take it, go back over to this side, mass is equal to N times capital M. Plug it in, 0.005912 ... moles times our molar mass, which is 325.3 grams per mole. Moles cancel out, we'll be left with the mass. 3 sig digs for this particular question again. The mass of the lead 2 acetate is officially equal to 1.92 grams. And there you have it, guys. Not just simple stoichiometry, but gravimetric stoichiometry. Stoichiometry, which you now need to incorporate mass. There's definitely some questions you can work on with this. And you should absolutely work through them all, please. Guys, potentially this will take a fair bit of work. So don't leave this till Saturday or Sunday. And if you already did, well, shame on you. You should know better by now. So work through it. Work hard. Here we go. Do 1, 2, all, and 3. And I'll talk to you again soon in the next podcast. Let me know if you got questions.